Hello, we are Team Rite-Solutions, and our project was the Virtual Reality Bridge Trainer. Our technical directors were Thomas Santos, Michael Von Gonen, and Akintoye Onikoye. The team consisted of myself, John Bevilacqua, computer engineer, and my partner, George Bowen, also computer engineer. To give a quick company overview of Rite-Solutions, they're a company based in Middletown, Rhode Island. Their motto is Friends Enjoying Work, and they work with government and commercial clients to give them the information advantage with their solutions in software development, systems engineering, information technology, and learning development. The project motivation: a lack of available training facilities and resources have been identified as a key contributor to accidents at sea. Rite-Solutions wanted to address this issue with a standalone portable training system. The anticipated best outcome for this system was a realistic and immersive virtual reality training program with realistic ship handling physics, secondary contacts, and accurate Rhode Island geography and navigational aids. The application had to be able to run on a laptop and had to be able to accommodate use of other hardware and software and be able to be expanded with upgrades and support for more training scenarios in the future. We are happy to report that the ABO was achieved. To give a summary of the key technical accomplishments of the project, we set up the development tools necessary to create the application, implemented virtual reality into the project, implemented ship handling physics, implemented the secondary display view for the evaluator and the GUI for the evaluator, secondary contacts, and 3D assets for both the Rhode Island geography, ship models and sprites, and weather. With the success of the project, Rite-Solutions hopes to expand their training capabilities into virtual reality and demonstrate the new emerging technologies with virtual reality and applications such as Unity to develop projects such as this. To quickly go over a block diagram for the project, we have two main hardware pieces: the laptop running the application and the HTC Vive, which is a virtual reality headset. We have two users, one using the laptop and the other using the headset. The inputs from the headset go into the Unity game engine through an API called OpenXR, and all inputs go through Unity's input system. And from the Unity game environment, from the running application, we have two outputs: the evaluator GUI to the laptop display, and the actual 3D simulation to the operator's display in the VR headset. My individual technical contributions for the project were the virtual reality implementation, ship handling physics, evaluator view, and weather. First, to quickly go over the development environment that made this all possible. Unity is a free-to-use game development engine. The key features it provided for the project were its multi-platform support, real-time development, extensive C# based scripting API, and virtual reality support. For our virtual reality implementation, we chose to use OpenXR. OpenXR is an open API standard for both virtual reality and augmented reality. It too has multi-platform support, not just for operating systems, but also for hardware, meaning our application worked not just with the HTC Vive headset that we had, but also with other headsets such as the Valve Index and the various Oculus VR headsets. In Unity, the XR origin allowed us to control the VR playing space and camera in the application, and the XR interaction manager handled inputs from the virtual reality headset and controllers using Unity's input interaction system. For the ship handling physics, the ship movement was implemented through the Unity physics module using the rigid body component. We gathered data for submarine acceleration and deceleration, as well as tactical diameter, and used that to create an accurate model of its movement within the Unity simulation. In the application, on the left, through the own ship GUI, desired orders for port or starboard rudder angle, course, or speed and knots can be input, and when the send orders button is pressed, that data is sent to the submarine in the simulator, which moves accordingly based on what orders it received. To accomplish this type of relationship, we needed to have multiple displays running from the same application. Our primary display is for the operator, which goes to the VR headset, and the secondary display is for the evaluator, which displays on the laptop screen, which allows the evaluator to both place secondary contacts as well as send orders for the own chip. This was accomplished using Unity's built-in display system, setting two displays, one for the VR headset camera and the second for the evaluator GUI. Another example of the relationship between the evaluator GUI and the simulation is the weather. Through the weather GUI menu, the evaluator can enable rain, snow, or fog, which appears in the simulation, obscuring the operator's view. The rain and snow were created with Unity's particle system, and the fog was created using the built-in fog feature for scenes in Unity. I will now be passing things over to my partner, George Bowen, to talk more about the evaluator GUI, as well as secondary contacts and 3D assets.
To start, here's an overview of what I've accomplished across the fall and spring semesters. I created a cloud build of the Unity project, various aspects of the evaluator GUI, including a functional real-time map in the two main menus, a working start menu, various parts of the secondary contact spawning features, the entire Rhode Island geography model, imported chip models, and created sprites and buoy models. The Rhode Island geography model was a task that took me around half of the spring semester to complete, as numerous resources had to be utilized. Towards the end of the fall semester, when we first started thinking about creating geography models, I found a model for sale on cgtrader.com made by City Art that had an accurate coastline and included buildings for the entire state of Rhode Island. At the time, the model was $100, and there was no pressure to get a model of the entire state implemented yet, so I bookmarked it and looked for other resources. The next tool I found was a website called Touch Terrain, which allows you to select a rectangular area of the world, and the site uses topographical satellite data to create a 3D model of the state. After numerous tests utilizing different settings, I arrived at a sufficient geography model of the state. After importing the model into Blender, I first had to delete parts of the mesh that represented the water, as there was no undersea elevation data. The next challenge was to implement buildings along the coast. Numerous resources were considered, including the Bing Maps SDK and a public GitHub repository that uses Google Maps to create 3D models. But the roadblock for both of these methods is that there isn't sufficient 3D data for Rhode Island to utilize for these models. Because of this, the team agreed to purchase the Rhode Island model available on cgtrader.com, now $75 after inspection. The one drawback of this model is that the land portion is completely flat. For this, the solution was to essentially combine the model along with the touch terrain model. I imported the two models into the same Blender project, scaled them, aligned the masses as best as I could, and manually moved each building along the coast onto the touch terrain model. Due to the intended area of use for this project and the lack of sufficient time remaining in the semester, our technical directors were content with this process being done for the coasts of Connecticut Island and the west and south coasts of Aquidneck Island. Next, I looked to implement a grass texture to the touch terrain model. The most common method to apply a texture to a model is using an image texture. However, the touch terrain model was too large, and stretching a single image across such a large model did not yield great results. Instead, I used a method called texture tiling, which is done through the shading tab of Blender. Essentially, using a combination of Blender shading nodes, the grass texture image I found online was applied onto the touch terrain model in a grid pattern. This single image repeating itself, however, resulted in a very repetitive pattern, so I used this method with two different grass texture images and combined them, resulting in a more varied looking grass texture. The last major details to be implemented for the geography were the Jamestown and Newport bridges. Thankfully, I was able to find a model for each bridge available for free on SketchUp.com. Since these models were only available as SketchUp files, however, I had to jump through numerous hoops to add them onto my Blender file, but I was eventually able to do so. As for the water, I used Crest, an advanced ocean renderer available on a public GitHub repository. This repository provides all of the necessary assets to implement a realistic water simulation. Our first thought when approaching ship models was that not only were John and I not experienced enough in Blender to create ship models, but that it also wouldn't be worth our time to try and create our own models when there were likely a great deal of free models available online. This turned out to be true, and after consulting with our technical directors, we downloaded 5 different ship models, including a submarine, merchant, small craft, trawler, and sailboat. Each of these models were first imported into Blender, where they were scaled to our technical director's desired size, appropriate rotations were applied, and then imported into the Unity project. One of the last things I implemented into the project were buoys. Unfortunately, there were no suitable buoy models available online, so I created them myself in Blender. Once these models were finished, I imported them into the Unity project, made them prefab objects, and then I used the Nautical Charts tool on the National Oceanic and Atmospheric Administration, or NOAA, website to place buoys in the appropriate locations throughout Narragansett Bay. One of the first features I implemented was the evaluator GUI map. As you can see on the left, the operator's ship is moving in the 3D Unity environment, and in the evaluator GUI on the right, its movement is reflected on the map in relation to the geography. For this feature to work, I created a script that computes the distance between the operator's ship and any potential obstacle, and converts that XYZ distance vector into an XY vector, which is then applied to the minimap object on the UI canvas. The operator's ship sprite is centered on the map, and all movement is reflected in the sprite's distance from each individual obstacle sprite, including the large geography sprite, which is essentially a top-down picture of the entire Rhode Island Blender model. Additionally, I added a zoom slider, which effectively enlarges or shrinks each sprite except for the operator's ship sprite, while still accurately reflecting each obstacle's relative distance to the operator's ship. In order to have a functional map, there needed to be sprites to represent each potential obstacle for the operator. I created each of these sprites myself in Affinity Photo and include the operator ship or own ship, secondary contacts including trawler, small crafts, sailboats, and merchants, buoys, warships, submarines, and airplanes. One of the most important features of this application is the ability for the evaluator to spawn ships or secondary contacts for the operator to safely avoid. First, we implemented the ability to spawn single contacts. I created a menu that provides all of the necessary functionality to spawn a contact, including a drop-down menu to select what class of ship to spawn, along with presenting a picture of each ship as you select it, and your desired course and speed for the contact. The course and speed has been applied using John's player script he mentioned earlier. Once these options have been filled out, there are 2 methods to spawn the contact. The first, more simple method is to enter your desired latitude and longitude, or in this case, the X and Z coordinates in the Unity environment. After clicking Apply, the ship will be spawned and its corresponding sprite will be added to the evaluator GUI map. The second, more intuitive method is to simply click on the map where you would like the ship to spawn. To add this feature, I essentially use the minimap functionality in reverse. The script takes the distance from your click's location to the operator's ship sprite and converts that to XYZ coordinates in the 3D Unity environment and then spawns the ship there. Once single contact spawning was completed, it was time to work on contact groups. The 2 different kinds of groups that our technical directors desired were fishing circles and merchant transit lanes. Upon accessing the group secondary contact menu and selecting the fishing circle option, you have 1 setting to fill out, which is the number of ships you would like to spawn. Then you will have to click on the evaluator GUI map twice. The first click determines the center of the circle, and the second determines the radius of the circle. Once these values have been determined, a specific number of random XZ coordinates, determined by your desired number of ships, is generated within the circle, and a trawler model is spawned at each of those coordinates. To make this process more intuitive, John implemented the visualization feature, which creates a circle on the evaluator GUI map and automatically resizes between your first and second clicks, allowing you to see the size of your fishing circle. If you select the merchant transit lane option, you are given 2 settings to fill out: ships per hour and speed, which determines how many ships you would like to spawn per hour and how fast you would like them to be moving upon spawning. Then you have 3 clicks to make on the map. The first determines the starting point of the lane, the second determines the length of the lane and the direction that the ships will be moving, and the third determines the width of the lane. John also implemented the visual feedback for this process as well. After the third click, a single ship is spawned randomly along the width of the starting edge of the lane, moving at your desired speed, and a timer is initiated which will be used to determine when it is time to spawn the next ship. The merchant transit lane is a bit different from fishing circles in that it essentially requires a function running endlessly through the simulation. You can't have a single function in one script to continuously spawn ships on a timer if you want multiple transit lanes, so the script was attached to an empty object and turned into a prefab. That way, whenever you want to create a transit lane, it spawns a new instance of the script, allowing multiple lanes to exist in the same simulation. At the beginning of the year, we promised a realistic and immersive virtual reality training program with the ability to effectively train maritime operators how to handle and navigate their ship under various conditions, to include abnormal weather, high contact density, and visual-only navigation through Rhode Island's Narragansett Bay. After 6 months of hard work, we are pleased to declare this outcome as a reality. We would like to thank our technical directors from Rite-Solutions, Thomas Santos, Michael Von Gotten, and Akintoye Onokoi, for the opportunity to work on this great project and for their continued support throughout the past 2 semesters. Additionally, we'd like to thank Brendan Smearbeck and Jack Murphy for the resources they provided us, along with the work they put into the Capstone program. Last but not least, we would like to thank Dr. Sunak for all of the work he's done that has made the entire Capstone program possible. Working on this project has been a real privilege for John and I, and has truly done a great job in preparing us for a future career in the engineering field. Thank you.